Look at your hands. Turn them over. See the lines, the creases, the shape of the bones beneath the skin. They feel solid, do they not? They feel real. You can clap them together, and they meet with a definitive, satisfying report. A sound that confirms their presence, their substance, their undeniable thingness. You can press a fingertip against a tabletop, and the table pushes back. It resists. It is there. You are here. A clear boundary exists between the two. This is the first and most fundamental story you have ever been told. It is a story your senses whisper to you from the moment you are born. A story of objects, separate and distinct. A story of substance and void, of things and the empty spaces between them. It is the story of a solid world. And it is a lie. A beautiful, intricate, and necessary lie, but a lie nonetheless. It is a convenient fiction crafted by evolution to help you navigate a world of predators and prey, of falling rocks and nourishing fruit. It is a user interface for reality, simplified for the sake of survival. But beneath this interface, beneath the illusion of solidity, beneath the very concept of a thing, lies a reality so strange, so vast, and so utterly counterintuitive that it dissolves the world you think you know into a shimmering, uncertain sea of potential. To find it, we must let go of the idea of a thing. We must unlearn the comfort of the solid and embrace the truth of the ethereal. We must look past the particles and listen for the music that they are made of. Or are you really? If you're not the solid, definite object your senses report you to be, then what is the alternative? You're a ripple, a pattern, a resonance. You are a disturbance in an invisible ocean that permeates all of space and all of time. An ocean that has no shores and no floor. An ocean that is everywhere at once. This ocean is called a field, and it is the only thing that is truly real. This is not poetry, though it sounds like it. This is not a metaphor, though we must use them to speak of it. This is the bedrock of our modern understanding of the physical world. It is the deepest truth physics has yet uncovered. The universe is not made of tiny, hard balls of matter. It is made of fields. An electron is not a thing. It is a localized vibration in the electron field. A quark is not a tiny speck. It is a concentrated excitation in the quark field. A photon of light is not a discrete bullet. It is a quantum ripple in the electromagnetic field. Every particle that makes up your body, the air you breathe, the star that warms your face, every single one of them is nothing more and nothing less than a momentary, localized note played upon the immense, invisible instrument of its underlying field. There's an electron field. It fills the universe. It is in the space between galaxies. It is in the heart of the sun. And it is inside you. It is one single, continuous entity. The electrons in the atoms of your left hand are vibrations in the exact same field as the electrons in the most distant star we can see. They are not separate things. They are connected patterns on a single cosmic tapestry. Think of a vast, still lake stretching to infinity. This is a field in its lowest energy state, what we might call the vacuum. Now, tap the surface of the lake in one spot. A ripple forms, a little pulse of energy travels outwards. That ripple is a particle. It has energy. It has momentum. It can interact with other ripples. But it is not made of something other than the lake. It is just the lake doing something in a particular place. This is the world. This is you. A complex, stable, interacting collection of ripples on the surface of a dozen or so fundamental fields. This changes everything. It changes the meaning of empty space. It changes the meaning of matter. And it changes the meaning of you. The journey to this understanding was not a straight line. It was a chaotic, reluctant stumbling towards an unwelcome truth. Science in the late 19th century was confident. It had mapped the world. Newton's laws governed the majestic dance of the planets. Maxwell's equations had unified electricity, magnetism, and light into a single, elegant framework. The world was a great clockwork mechanism. All that was left, it was said, was to fill in the last few decimal places. But the clockwork was starting to stutter. There were ghosts in the machine, a strange glow emanating from vacuum tubes, a puzzling radiation from certain kinds of rock, and a deep, intractable contradiction at the heart of it all. The universe, it seemed, was schizophrenic. It obeyed two different sets of rules. On the grand scale of stars and planets, Einstein's newly forged theory of general relativity described a smooth, curved, deterministic spacetime. Gravity was not a force, but the shape of the universe itself. It was a theory of sublime, geometric beauty. But on the tiny scale of atoms and their constituents, a new and bizarre theory was taking shape: quantum mechanics. This was not a world of smooth curves and predictable paths. It was a world of jumps and probabilities, of uncertainty and paradox. A world where a particle could be in many places at once until you looked at it. A world that seemed to be governed by the roll of cosmic dice. The two theories were both spectacularly successful. Relativity gave us our understanding of the cosmos, of black holes, and the Big Bang. Quantum mechanics gave us lasers, transistors, and the entire digital age. But they could not both be right. At least, not completely. They were fundamentally incompatible. They spoke different languages. Relativity was a fluid, continuous poem. Quantum mechanics was a jagged, stuttering verse. How could reality be both? How could the universe be a smooth, deterministic fabric at one level and a chaotic casino at another? This was the crisis that consumed physics for decades. The search was on for a theory of everything, a deeper framework that could unite the two warring descriptions of reality. The first steps were taken not by trying to merge them, but by trying to perfect one of them. The problem was with quantum mechanics. While it was brilliant at predicting the outcomes of experiments, it had a hole in its heart. It described particles, but it could not account for their creation or destruction. And it was haunted by Einstein's relativity, which demanded that nothing, not even information, could travel faster than light. The simple quantum theory of the 1920s didn't respect this cosmic speed limit. The puzzle pieces were on the table. Quantum mechanics, with its probabilistic particles. Special relativity, with its unbreakable light speed barrier. And Maxwell's theory, which had already described light as a wave in an electromagnetic field. It was a young, almost mystically inclined physicist named Paul Dirac who first saw the path forward in the late 1920s. He was a man who famously claimed that it was more important to have beauty in one's equations than to have them fit experimental data. He sought a beautiful equation, one that would describe the electron in a way that was consistent with both quantum mechanics and special relativity. What he found was more than he bargained for. His equation was beautiful, stunningly so, but it was strange. It had two solutions. One described the electron as expected. The other seemed to describe an impossible particle, an electron with positive charge and negative energy. It was a ghost in his mathematics, a nonsense result. Lesser minds might have discarded it, tweaked the equation to make the ghost go away. But Dirac trusted the beauty of his math. He took the ghost seriously. He proposed that for every particle, there must exist an antiparticle, an identical twin with opposite charge. He predicted the existence of antimatter. A few years later, in the cloud chamber debris of cosmic ray collisions, his ghost was found. The positron, the anti-electron, appeared exactly as his beautiful equation had demanded. It was a triumph, but it was also the first clue that particles were not the fundamental actors in the drama. Dirac's equation did something else, something even more profound. It treated the particle and the space around it as parts of a single system. It hinted that the vacuum of space was not empty. It was a sea of potential from which a particle and its antiparticle could be born if you hit it with enough energy, and into which they could annihilate each other, vanishing back into the potential for which they came. The idea of the field began to crystallize. Perhaps the particle was not the thing. Perhaps the field was the thing. The particle was just what happened when you disturb the field. This was the birth of quantum field theory, the grand synthesis, the idea that you could take the quantum rules of probability and uncertainty and apply them not to little billiard balls, but to continuous, omnipresent fields. The consequences were immediate and profound. Suddenly, particles could be created and destroyed. An excitation in a field could transfer its energy to another field, creating a new excitation, a new particle. An electron and a positron, ripples in the electron field, could collide and vanish, their energy creating two new ripples in the electromagnetic field, which we call photons. It was a theory of transformation, of birth and death, all governed by the interactions of these underlying fields. It also solved the problem of spooky action at a distance. How does one electron know another is there to repel it? In the old view, it was a mysterious, instantaneous force. In quantum field theory, it is a local interaction. The electron, a ripple in the electron field, creates a disturbance in the surrounding electromagnetic field. This disturbance, a virtual photon, travels outwards at the speed of light and jostles the electromagnetic field in the vicinity of the other electron. That electron, being a ripple in its own field which is sensitive to the electromagnetic field, is then pushed away. There is no spooky action. There is only the rippling of interconnected fields, a message passed from one to another according to the strict laws of locality and the cosmic speed limit. But the theory, in its infancy, was sick. When physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tominaga tried to calculate the results of these field interactions, their equations broke down. They kept running into infinities. The energy of an electron interacting with its own field would calculate to be infinite. The probability of certain events would be greater than 100%. It was a mathematical catastrophe. The theory was elegant and powerful, but it gave nonsensical answers to the simplest questions. It was like a beautiful car with an engine that exploded the moment you turned the key. For years, the best minds in physics struggled in a state of deep depression and confusion. They had this incredible idea, this glimpse of a deeper reality, but they could not make the math work. They had to invent clever, ad hoc tricks to sweep the infinities under the rug, a process they called renormalization. It was like saying, well, we know this part of the equation wants to be infinity, and we know the final answer is a small number we can measure in the lab. So let's just subtract one infinity from another and hope it works out. It felt like cheating. Feynman himself called it a dippy process. Dirac, the theory's grandfather, hated it. He saw it as papering over a fundamental flaw, a sign that the whole idea was still deeply wrong. And yet it worked. It worked with unbelievable, stunning precision. Once the infinities were swept away, the predictions of quantum field theory matched experimental results to an astonishing number of decimal places. It was the most accurate scientific theory ever devised by humankind. It was as if a composer had written a symphony with a dozen screeching, out-of-tune notes, but had left a note in the margin saying, just ignore those, and when the orchestra did so, the result was the most beautiful music ever heard. How could this be? How could a theory that was so obviously mathematically flawed be so powerfully prophetically right? The answer would come decades later, with a deeper understanding of what a field truly is. The infinities were not a mistake in the theory. They were a clue. They were the mathematics screaming that our simple picture of a point-like particle was wrong, that a field's behavior changes depending on the scale at which you look at it. The bare charge or mass of a particle, if you could zoom in infinitely close, might well be infinite. But we can never see that. What we see is the dressed particle, shielded and cloaked by a cloud of virtual particles constantly bubbling out of the surrounding fields. The renormalization procedure was not cheating. It was the mathematics accounting for this quantum cloak of invisibility. So what are these fields that make up our world? We have discovered a surprising few. There seems to be a field for each fundamental type of particle. There is one electron field for all the electrons in the universe. It is a single, unified ocean of potential electron nests. There are fields for more exotic, heavier versions of the electron, called the muon and the tau. They are like heavier echoes, notes in a different octave, but played on a similar instrument. Why these heavier copies exist is one of the deepest mysteries we still face. Then there are the quark fields. These are stranger still. There are 6 of them, with whimsical names like up, down, strange, charm, top, and bottom excitations in the up and down quark fields are what come together in threes to form the protons and neutrons in the nucleus of every atom. But the quark fields are prisoners. They're governed by a force so powerful, the strong nuclear force, that you can never, ever see a quark by itself. The field that carries this force, the gluon field, has a bizarre property. The force it mediates gets stronger with distance, not weaker. It's like a cosmic rubber band. If you try to pull 2 quarks apart, the energy in the gluon field between them increases until it is enough to create a new quark and antiquark pair out of the vacuum. The new particles snap together with the old ones, and you end up with 2 pairs instead of 1 isolated quark. A quark is a ripple that can never leave its brothers. It is a note that can only be played as part of a permanent, inescapable chord. The very substance of your body's mass is built from these eternally confined vibrations. And what are forces? They too are fields. The electromagnetic field, whose ripples are photons, governs every chemical reaction, every nerve impulse in your brain, and the very structure of atoms. The weak nuclear field, whose ripples are the massive W and Z bosons, governs radioactive decay. It allows a quark to change its flavor, for a down to become an up, turning a neutron into a proton. It is the force of transformation, the alchemical engine at the heart of the sun, fusing hydrogen into helium and releasing the light that gives us life. And then there is the strangest field of all, the Higgs field. For decades, the standard model of particle physics, this beautiful catalog of fields, had a gaping hole in it. The equations only worked if all the particles were massless and flew around at the speed of light. This was obviously not true. You have mass. The chair you are sitting on has mass. Why? In the 1960s, a handful of physicists, including Peter Higgs, proposed a radical solution. What if all of space is filled with an invisible field, a kind of cosmic molasses? What if particles acquire mass simply by how much they struggle to move through this field? Particles like the photon feel no interaction with this Higgs field, and so they are massless and travel at the speed of light. Particles like the electron interact with it just a little, and so they have a small mass. Particles like the top quark interact with it very strongly, and so they are incredibly massive. Mass, in this picture, is not an intrinsic property of a thing. It is an acquired property. It is a measure of the friction a particle feels as it moves through the Higgs field. You are heavy not because you are made of heavy things, but because the fundamental fields that make you up are snagged on the omnipresent Higgs field. This was a wild, almost unbelievable idea. An invisible, universal field whose only job was to give everything else its heft. For nearly 50 years, it remained a theory, a necessary ghost in the machine of the Standard Model. Until, in 2012, at the Large Hadron Collider in Switzerland, physicists finally succeeded in hitting the vacuum with enough energy to make the Higgs field itself vibrate. They struck the cosmic molasses hard enough to make a ripple. And they saw it, the Higgs boson, a momentary, fleeting particle that was nothing less than a fragment of the field that gives the universe its substance. The ghost had finally appeared. So this is the world of quantum fields, a universe woven from a dozen or so of these invisible, energetic oceans. But the story gets stranger still. What is empty space? What is the vacuum? We think of it as nothing, the absence of things. But in quantum field theory, the vacuum is the most interesting place in the universe. A field, being a quantum object, is subject to the Heisenberg uncertainty principle. This principle states that you can never know certain pairs of properties, like a particle's position and momentum, with perfect accuracy. But it also applies to a field's energy. A field can never be perfectly still. It can never have an energy of exactly zero. The vacuum is not empty. It is simply the lowest possible energy state of all the fields. But that lowest state is not zero. The fields that fill all of space, even in the darkest void between galaxies, are constantly jittering, constantly fluctuating. The vacuum seethes with a roiling foam of virtual particles. For infinitesimal moments, a particle and its antiparticle can borrow enough energy from the vacuum to wink into existence, before annihilating each other and paying the energy back, all in a time so short it can never be directly observed. Empty space is not empty. It is a plenum of potential. It is a riot of creation and destruction at the quantum level. These virtual particles are not just a mathematical curiosity. They have real, measurable effects. They subtly alter the energy levels of atoms. They contribute to the mass of other particles. The vacuum has a weight, an energy density, and this vacuum energy may be the source of the mysterious dark energy that is causing the expansion of the universe to accelerate. The nothing of space may be what is pushing everything apart. Think about what this means. The ground of reality is not a static stage on which things happen. The ground of reality is a turbulent, dynamic, and endlessly creative medium. The distinction between matter and emptiness dissolves. Matter is just a particularly excited, long-lasting state of the emptiness. Where does this leave you? You, with your solid hands and your sense of self. You're built from this. The electrons in your atoms are stable ripples in the electron field. The quarks in your nuclei are stable, confined chords played on the quark fields. The photons that allow you to see these words are ripples in the electromagnetic field. Your mass is a measure of your field's drag against the Higgs field. Your very existence is a complex, self-sustaining pattern of interaction between these fundamental fields. You're not a thing made of smaller things. You're a process, a stable, harmonious dance of energy. Look again at your hand. It feels solid because the electron field that makes up the outer shells of your atoms violently repels the electron field that makes up the outer shells of the table. The force between them, carried by the electromagnetic field, is immense. You are not touching the table. You are being held at bay by the furious repulsion of invisible fields. What you feel as solid is just the clamor of these fields refusing to occupy the same space in the same way. Solidity is a force field. You're also mostly empty space. But that emptiness is not nothing. It is a seething cauldron of all the fields, fluctuating and bubbling with potential. You are a pattern of excited fields, walking through an ocean of quiescent fields. And what of the self? The I that is reading these words? The consciousness that experiences this reality. Science cannot yet answer this question. It is the great frontier. But quantum field theory provides a new and powerful language with which to ask it. If you're a pattern of field excitations, then what is your consciousness? Is it an emergent property of the fantastically complex pattern of electromagnetic field activity that is your brain? Is it a particular kind of resonance, a standing wave of information that has achieved self-awareness? The theory suggests a radical interconnectedness. The electron field in your brain that participates in the firing of a neuron is the same electron field that stretches to the Andromeda galaxy. It is one indivisible whole. The fields that constitute you are not contained within your skin. They extend, in principle, to infinity. Their influence diminishes with distance, of course, but it never truly reaches zero. In a very real, physical sense, you are not separate from the universe. You are a local, complex modulation of the universe itself. You are the cosmos experiencing itself. This dissolves the classical notion of the observer and the observed. In the old quantum picture, there was a strange problem. A particle existed in a cloud of probabilities until a conscious observer looked at it, at which point it collapsed into a single, definite state. This gave consciousness a strange, almost magical role in the creation of reality. Quantum field theory offers a more sober, if no less profound, perspective. There is no special observer, there is only interaction. Your measuring device, your eye, a particle detector, is also made of fields. When it interacts with an electron field, the fields couple together. The system of electron field plus measuring device field evolves. The diffused ripple of the electron becomes localized not because a mind commanded it, but because of a physical interaction with another set of fields. The universe is a closed system of interacting fields. We are not outside observers looking in. We are inside, part of the interaction. Our act of measurement is not a magical invocation. It is one part of the universal dance touching another. Reality is not something that waits for you to look at it. Reality is the ongoing, ceaseless interaction of everything with everything else. So, are particles real? Is an electron a real thing? The question itself is a relic of our old way of thinking. It's like pointing to a wave crest on the ocean and asking, is that wave a real thing? Well, yes, it has properties. It has height, speed, energy. It can knock you over, but it has no independent existence. It is not a thing made of some special wave stuff. It is just the water of the ocean moving in a particular way for a short time. If you try to scoop up the wave in a bucket, you just get water. The waveness was a property of its dynamic form, its pattern of motion. A particle is the same. It is real in the sense that it is a real pattern of behavior of a field. It has measurable properties. It could do things, but it is not an independent entity. If you try to grab an electron, what you're doing is interacting with the electron field. The particle is a temporary, localized manifestation of that field. The field is the fundamental reality. The particle is the story the field is telling. This perspective is profoundly liberating. It frees us from the tyranny of the object. We are not static collections of matter. We are temporary, flowing patterns. We are like whirlpools in a river. A whirlpool has a definite shape and structure. It can persist for a long time, but not a single water molecule in it is permanent. The water flows in, participates in the pattern of the vortex, and flows out again. The whirlpool is a stable pattern, not a stable collection of stuff. You are a whirlpool of field excitations. The energy and matter that make you up are constantly being exchanged with your environment. You eat, you breathe, you radiate heat. The atoms in your body are replaced every few years. You are not the same physical stuff you were a decade ago, but the pattern, you persists. You are the form, not the substance. What does it feel like to be a pattern? It feels like this. It feels like memory, hope, love, and the experience of reading these words. It is the coherence of the pattern that we experience as a continuous self. This view also offers a new kind of humility. The universe is not a collection of resources for us to use. It is a single, interconnected entity of which we are a small, temporary part. The fields that make us are the same fields that make the stars and the nebulae. We are akin to the cosmos in the most intimate way imaginable. Think of the vastness this implies. There's a field called the muon neutrino field. It permeates everything. Trillions of ripples in this field, created in the sun and distant supernovae, are streaming through your body right now, every second. They barely interact with the fields you are made of, so they pass through you, through the entire Earth, as if you were not there. You are simultaneously a dense, complex pattern and almost completely transparent to other aspects of reality. The universe is layered, woven from these different fields, most of which are ghosts to one another. What we perceive as reality is just the set of fields with which our own fields happen to interact strongly. It is a tiny slice of the full, multidimensional richness of existence. What other fields might there be, whose particles we cannot detect? What other symphonies are being played, unheard, in the same space that we occupy? Our standard model is likely incomplete. The mystery of dark matter suggests the existence of at least one more field, perhaps more, whose ripples have mass and shape the galaxies, but which barely acknowledge the existence of the fields that constitute us. We live in a haunted house, surrounded by invisible presences whose gravitational influence is the only sign of their existence. We are left in a state of profound and beautiful uncertainty. We have peeled back the illusion of solidity to find a world of shimmering, interconnected fields. We have learned that emptiness is full, that matter is a pattern, and that we are not separate from the cosmos, but are a way for the cosmos to be aware of itself. What is the ultimate nature of these fields? Are they the final layer of the onion? Or are they too an emergent property of something even deeper and more bizarre, like the vibrating strings of string theory or the discrete pixels of space-time in loop quantum gravity? We do not know, but the step from a world of things to a world of fields is the largest philosophical leap that physics has ever asked us to make. It asks us to abandon our most basic intuitions. It asks us to accept that the universe is fundamentally a verb, not a noun. It is a happening, not a place. So let go of the idea of your hand as a solid object. See it for what it is: a temporary, intricate knot of vibrations in a universal, invisible ocean. A fleeting chord in an eternal symphony. The fields within it were forged in the first moments of the Big Bang, and they will persist long after the pattern that is you has dissolved. You are not a vessel containing a piece of the universe. You are a wave on the ocean of the universe. The wave rises, takes a unique form, holds itself together for a moment, and then falls back into the ocean from which it came. But the ocean remains. The fields are eternal, and the energy that made up your pattern is not lost. It simply returns to the whole, ready to become part of the next wave, the next star, the next whisper of reality. This is not an end. It is a continuity. It is the deepest form of belonging there is. You are not a stranger here. You are home. You are, and have always been, a part of the restless, creative, and magnificent sea of being. A melody the universe is singing to itself. Listen.